Welcome, everyone. Thanks so much for joining. I'm just here to quickly introduce our speaker and then we'll get going. So for those of you that don't know, I'm Mara Cairo, a product owner at Amii, and super excited to introduce Mehadi and Zehra this hour to talk about their work at Clinisys. Clinisys provides intelligent software solutions, data migration services, and data consulting expertise to healthcare research groups, hospitals, government agencies, clinicians, and private sector clients. Clinisys is a participant and service provider in the Ecosystem Project, an Alberta Artificial Intelligence Ecosystem Initiative supported by Amii and funded in part by Prairies Canada. The initiative brought together 9 organizations from nonprofit, business, and academia to establish viable uses for AI and machine learning in health and data analytics. We've been showcasing these organizations on our social media channels, so I encourage you to check out our LinkedIn to learn more about the other participants. But for now, I will pass it over to Mehadi and Zehra.
Thank you, Mara, for your kind introduction, and it's a pleasure to be here. Just give me 1 sec so that I can, if you can see my screen, let me know.
Yeah, it looks good.
Perfect. And I'm going to move this a bit because I need to start the slideshow. It's always challenging to work on from one screen, but anyhow, here we are. Okay. So first and the foremost, thank you so much for this invite, and we are proud to be the participants in the ecosystem project, as well as working with Amii, and of course UFA. We were fortunate to have Zehra Shah, who is going to do the second part of my presentation here, and she is a PhD candidate at UFA under Dr. Russ Grainer. He was kind enough to provide expertise as well as allow Zehra to work on this project. So that's we are very thankful to UFA as well. With that, I'm going to talk a little bit about the company and the type of business cases or use cases, how we arrived at, or what kind of thought process was there. A little bit of a history about Clinisys and what we have been doing in for last 10 years or so, and then I'll hand over the slides to Zehra to talk more about the technicality of the projects that we worked on. With that, the first slide here talks about mostly what Clinisys is. So we started our operations in 2011. We were founded here in Edmonton with an intent to work in data analytics and mostly in visualization of healthcare data. That was the idea. So it was founded by medical IT professionals and so forth. But we also knew that most of our data has to come from primary source, or what we call primary care. For that purpose, we also went into, or rather we went very precisely into medical records. And so we came out with a product called Clinisys EMR, which is the electronic medical record used by physicians, specialists, hospitals as well, and so forth. So that's what has been our history. Our foundation has been from the medical record data, and that's why we also have a product that we sell in the market that is used by physicians in 4 provinces in Canada. And now we just rolled out last month in Mexico a Spanish version of the EMR system. So that has been our brief history. I'm just saying 2 lines about the history, but it has been 10 years. And during those 10 years, we have been consistently working in data science projects. So that is important, that why we existed, why we were formed, and how we actually came about, while bringing a couple of products to the market that also generates revenue for the company, and we can progress the way we are. So we have various forms of EMR. So we have physician office EMR, we have allied health EMR. We also provide health data analytics services, as Mara mentioned in the introduction. And we also have something called patient portal. And now we have added the telemedicine to it, because the last 2 years have been very hard on patients and physicians. So, we collaborated with Microsoft to add Microsoft Teams into our EMR system. So that has been working well there on that front. We are built on very newer standards. So there are many EMR companies around 25, 26 to be prominent in Canada. But having said that, the later you come into the market, the more newer standards you are going to bring for your data. And so we are built on the newer data models or the new data standards, I would say, as far as our products are concerned, especially the EMR systems. So two use cases I'm going to present here today, purely from the business side, that how we approach the things and what we have done so far, both in EMR side and on the analytics side. So bear with me, I'll be going back and forth between the electronic medical records, which is the patient data, and hospital administration data, a little bit different, which Zehra is going to go a little bit more deeper into it. So this is the first use case, which is the medical records data. So what consists of the data, and I would just pardon myself, or please excuse me, I'm sorry that some of this information may be redundant for some of the knowledgeable people who are there on the call. But a patient system, or what we call an EMR system, consists of many different verticals. Scheduling is one, administration is another, the clinical patient record is third, and so on and so forth. It just goes on and on, the labs, the prescriptions, and so forth. So it just compiles quite a bit. Demographic itself is quite a bit of information when you try to collect the data. As we see in COVID scenario, the demographic information is so relevant. So here is a dashboard. I've just given a very quick preview of it. For a system that is being typically implemented in a clinic. So a clinic has an administrative role to see how the clinic is doing, how many patients are there, how many patients are coming today to see the doctors in the clinic, how many patients are active, how many patients are non-active, how many referrals we are talking about, how many walk-in appointments we are talking about today, and so on and so forth. So, a day, a snapshot of a day, I would say, is a dashboard for an administrative person who generally, when we walk into a clinic, we see these persons attending us first. These are the first line of contact, what we call in general physician office. I'm not talking about the hospital. I'll come back to the hospital later on. It's an emergency department, there we go. But if you see a typical touch point when we go in, now, we see from the data science perspective, each of these points as a data point. So if I'm a patient, I will have my own record. I will have my own date of birth and age and my name and my address and so on and so forth. So, it just expands from there for my demographic purposes. For the physician who is attending to me, we'll see it from how many patients he or she is going to attend to and whatnot, and so on and so forth. And is there a capacity? Is there a wait list? Is an overwhelming amount of patients which are coming in, and so forth. So this dashboards actually, as you can see, pulls in a lot of this information, because the front desk staff has to be on top of things if the clinic is really busy. If the clinic is not busy, then it is null and void, but otherwise it's a good point. The next one is what I was talking about, the patient demographic. So again, you can see how many data points a single demographic record is generating. Massive. Okay, so you have your healthcare number, you have the date of birth. If you're in Manitoba, they have a card that has an expiry date, where it is, how it is effective and whatnot. If you're in Ontario, you have a different number. If you're in Alberta, you are a different number, and so forth. So all these data points are collected in an EMR system. That is very vital, and I'm going to come back to it, why this is very vital when you try to collect this data, when you try to analyze this data. Just the demographic data and nothing else. Okay, but still quite a bit of data points. A single demographic file may have up to 60 data points, plain and simple, and some are very measurable, some are purely text, and some are dates, and so on and so forth. As you can see, it's a variety of data that we collect on EMR systems. Further complex case here. is a care plan. So let's say that I'm an acute care patient. I'm a diabetic, for example, and I have to measure my lifestyle, my A1C, how am I doing? If I am a cancer patient, then it is much more complex. If I am a heart patient, it just adds on to things and so forth. If I'm a child, for example, in terms of demographic, then what is my growth chart and how am I doing in terms of as a patient and so forth. So that also is collected. As you can see, action plan, lifestyle, diagnosis, appointments, all this data is collected at an EMR level, whether at the hospital or whether at the clinic level. Now, I'm not talking about whether these things talk to each other or not. That's not the topic here. Just that this data is collected and quite regularly collected for last, as I can think about 15, 20 years. This data has been collected at the front office of physicians or in the hospitals. Here is another very interesting example. This is a lab result of a particular patient. So we have actually deprecated the identifiable data here. So we have taken off the name and age and what, but this is a real record. It is called an HL7 record, which goes system to system. The system reads it, and it also denotes whether the range of this reading for this lab result, WCB or hematology, is beyond or within the range of prescribed normal or abnormal result. No intervention of human being is there. It is purely an HL7 file that gets into the system. It identifies whether it is good, bad, or ugly, But you can see the data points. A single requisition, when you go to a physician office, they may send you for lab results or, blood work, and that generates a lab result, which may have, again, 50, 60, 100 points, data points, as we say, depending on how many tests have been prescribed. Again, that is collected in the medical record system and electronically available to be analyzed at when it is needed to be. One more example, it's a prescription data. So for prescription, when we get to the physician office, either they will prescribe a medication or they will generate a lab requisition or both, or they will refer us to a specialist and whatnot. So here is an example of prescription. Again, a single patient can have multiple prescriptions. They can be on a continuous prescription model, or they can be once in a while you get sick and you got prescribed and you're good with it. But it will, that record is also there. And as you can see, many data points, what medication was prescribed, what was the quantity, type of medication, what was the frequency, and so on and so forth. So date and everything is collected in the system. And that also becomes a very vital part of the medical record. This is, now we are talking about a very detailed clinical analysis part of the game as far as the EMR system is concerned. So every time we visit a physician, this is the type of information they collect. So they call it subjective objective assessment plan, and also remark. This is very free text, or we call loose text, which is being collected. This is textual data. There is now why I'm showing this screen is that this may be, I'm not a computer scientist, but this may be a good candidate for NLP, for example, natural language processing, because this will be a textual data. Imagine hundreds of thousands of patients of, that this data has been collected over a number of years. You have a treasure of this data as well in EMR systems. This is more measurable data. So let's say that if I go to a visit, they check my weight, what is my blood pressure, systolic, diastolic, what is my pulse, all that, say oxygen saturation, for example, BMI, they measure, and this is very numerical data as far as, in simple words, in layman terms, if I would. What is my weight as well? All that is collected, and that can be analyzed as well as far as the patient charts are concerned. Here is another example of visualization of that kind of data. So if you have BP, pulse, weight, and BMI, very quickly, the systems, such as the EMR systems, modern systems that have layered built on it with data analysis, can see how the patient has been faring on a certain medication, has his or hers blood pressure is going up, down, whether his or hers BMI is doing well or whatnot, you know. Very forward-looking example. This screen was built, by the way, before COVID hit, but it became more relevant after the COVID hit. So this is one of our developers actually went out of his way and developed something called a patient map. Now, what happens is that whenever whenever the patient comes to the clinic, when he or she is treated by a physician, they record something called ICD based on the ICD codes, which is, you know, they also get paid by that, of course, but it's a disease classification code that they identify. Now, this developer of ours, he was a master's student. He took up Google API and he layered the data of ICD codes and identified that if there is a flu outbreak in a particular segment of the city, you can identify these people very, very quickly. Okay, so now we are seeing during the pandemic that, you know, we are doing some modeling and whatnot. You can very quickly identify through those APIs, which are freely or openly available, and overlay that. So overlaying of data is also becoming very big part of the modern or newer systems, where end users are interested in seeing if there is a particular quadrant of the city which is impacted by a particular disease. In this case, it was common flu. At that time when we developed, COVID was not even a reality. So now with COVID, this becomes a reality if someone is tracking or trying to track COVID patients in a particular quadrant, which is high or low. And we see that it's being done now. In numbers, very quickly, I'm going to go through this. A single clinic with 2 to 5 physicians may serve up to 20 to 40,000 patients. Imagine this. Okay, so you have, you know, just one clinic, and so every locality, every neighborhood has 1 to 2 to 3 clinics, depending on, you know, specialty and so forth. But GP clinics, we are talking about pretty much every nook and corner we find one. So just imagine the number of patients' data that is being collected. Now, of course, they may use different systems and so forth. That's not the discussion we are going into. But I'm just talking about the scope of the data that is being collected electronically, which has potential to be analyzed. Each patient may have multiple visits every year. So imagine this, you know, so 20 to 40,000 times 5, 10, how many times we go to see the physician. Clinical details, now we are diving further deep that I showed you, you know, the vitals are collected, the free text is collected, the lab results are collected, the prescriptions are collected, and I'm only touching very, very high level of details, but, you know, there's much more, you know, lab DI, which is digital imaging, is a subject by itself. You know, they could be collecting you know, CT scans or MRIs and X-rays and so forth. There is no end to it. Like it's a massive amount of data collection for a single particular patient can be collected. Each patient visit may result in multiple data points, as I said earlier, right? So every time you visit the physician, they will collect the data. Maybe there were only 2 or 3 points that they might be collecting, but it will generate one more record or one more page into your patient report. So how this data is collected is also important. A lot of it is standardized, a lot. I'm not showing all of it, but a lot is standardized. So I showed you the lab result. The lab result, the format behind the machine format of it is using HL7, which is health level 7. Digital imaging has its format, demographic has its format, of course, you know, which can be associated with HL7, you know. As well as patient record itself overall can be, you know, HL7 compliant. So import and export of the data becomes a little bit more, I would say, easier. ICD codes, as I said earlier, each disease is classified in North America by these standards, which is 9, 10, and 11 versions, various versions actually, depending on which province is using what version. But they're fairly standardized. And these classification of disease is international. So even when we were rolling it out in Mexico, we knew what classification they were using. There are other standards like Loink and SNOMED CT. These are more standards of HL7 related to HL7 actually. And that makes the HL7 more readable. As I said earlier, that the range of the abnormal result was already identified for the physician when he or she is looking at it, is red in color. Now that is being done by further layering of the standards like Loink and SNOMED CT. It can even identify if there is certain classified information on disease information. So for example, if someone has a CT scan for leukemia or something else, and if they find that it is positive, then it will say on the result, it is interpreted for the physician or the radiologist that this is already there. So those standards are becoming more richer as we go further, and as the technology advances. There are more newer versions of HL7 coming in, making it a little bit more easier for the physicians or the data scientists to analyze this data. Now, in terms of AI and ML opportunities, and here I'm going to actually very quickly hand over to Zehra, is where does the opportunities lie? As I say earlier, data analysis, time series, overlays. I showed you a map, integration. So we can integrate wearables and so forth, or bedside monitoring devices. Visualization is a very, very, very big part that we are finding. Physicians, clinicians, nurses, administrators, payers, insurers, everyone wants and likes visualization because they can have a very quick snapshot of the data. You can see how much data is collected. It is very difficult for a human eye to go through that much of textual data. So visual data will make it simpler. So that is one that we are seeing more and more projects around that. Decision support, as I said, if the decision is somewhat assisted, I wouldn't say we are not in the place where we are making the decisions. If we say that it's a decision support system, then we are purely going into AI, ML part of it where the diagnosis is done. That's the future. I'm not denying it's coming. But we are still in the part of developing those intelligence and models around that data that can automate as many processes. And that brings me to automation. So as I said, that if automation comes in, whether it is self-driving car, the same thing will be for the diagnosis. So if the data is collected constantly, and now we are in remote scenario, a remote environment, we are uploading our data through patient portals and stuff like that, then automation will be key. It is already happening, but it will be a key. Predictive modeling, that is Zehra, where she comes in with analytics and data science background. We saw predictive modeling in our COVID scenarios many times. We had models coming up and saying, well, if this is the hospital admissions rate, this is what's going to be in 5 months, 2 months, and so forth. That's more on the predictive side. R&D, of course, big thing. We have many projects that we have done in R&D with various institutions, UFA, Waterloo, and so forth, and we continue to do that. So there's a big demand in that area. And innovation. So as I said, integration with wearables, if my phone can do certain things for me to upload the data, download the data, view the data, that's one. Bedside device data integration. So, we can monitor those data and so forth and, go further in it. Some other terminologies around, as I said, time series analysis, data overlays, pattern identification, image analysis, radiology, and CT scans is a popular one that is coming more and more. Population health, of course, which we saw in COVID, historical analysis, real-time analysis, and predictive modeling. So these are, with this, I'm going to go to my last phase of my side of the presentation, which is what did we do on the hospital side. As I promised earlier, I'm only going to give you one example of the hospital. This was a 1-year-long project in Newmarket, Ontario. And what we did there was that they wanted to know how many patients were coming back in a hospital after they were discharged. again to be readmitted through the channel of ER, which is the emergency department. That's a very big dent in a hospital. When you go through an emergency system, it is very costly for the hospital. Okay, but imagine this. You've been discharged from an emergency department, and then again you go back to it within 24 or 72 hours. That drains the hospital. So they had the numbers, and they knew that this was the issue. But they wanted us to actually work on a project where we could track why these people are coming back. What is the reason behind it? And if there is any way that they can flag these patients who are more risk of coming back, more at a risk of coming back to the readmission. That's why it's called readmissions, hospital readmissions. And so we went on and developed something called a model for them. They were using something called a LACE algorithm to identify these patients, but they were doing after the fact, after they were discharged second time, third time. The LACE algorithm is fairly published algorithm. It's a score. And when a person has comorbidities and they have been admitted to the hospital, if they have too many comorbidities, and even if they're lucky, if they can find that person, and then they would apply that algorithm on that record, saying that L is for length of stay, acuity of admission, emergency department visit, and other parameters that they were measuring. And they would calculate and say, well, this person is very likely to come back, or this patient is not a risk, just treat him or her and then we will be good. So they were applying this algorithm, but they were falling short on two counts. One was that they were doing this analysis after the fact. So they wanted something, very quick tool that when a person enters the emergency department, they would apply the LACE score algorithm right there on the patient record and say whether this person is likely to come back. Okay, he or she has come for hypertension or a heart-related issue, but also has a cancer or some other underlying condition, and he or she might come back. So better to keep him or her a little bit longer instead of just after treating that one condition, release them. And so it was a very successful project. It was done over 1 year. And these are the steps we did. Some of the questions they had: how many patients are in the readmissions? What are the revenue implications on the hospital? How can we identify the high-risk patient before they come in? And how best we can treat the patient population. These were some of the questions we tried to resolve while working with the hospital administration there. And this is what the steps we took from the business side. I'm only talking, not talking technology, only talking business. The processes were identified, how we collect. This is a humongous amount of data. 1 terabyte data per month was that we were dealing with, only with relevant information, relevant to admissions and discharge, new algorithms. So we actually modified the LACE algorithm a bit, depending on what they wanted to do, and with their input and so forth. And a new user interface was developed for the ER department, where they can just plug in the number of their healthcare identifier, and it will say this patient has X amount of condition. If he or she is coming to the admissions, is a high risk patient or low risk patient, depending on. So they are prepared before the patient goes into the emergency department, if they intake it. So they are a little bit better prepared, and that would reduce their cost. With that, I'm going to turn over to Zehra, and I'm going to stop sharing the screen, and the questions we'll take after the presentation. Thank you.
Thank you, Mehadi. Let me go ahead and share my screen now. All right. Can everybody see my screen? Yeah?
Yeah, looks good.
Okay, great. All right, so I'll be talking about two, in fact, data analytics collaborations that we did. So one was with the Cross Cancer Institute. here in Edmonton. We did a hospital resource allocation project, and this is ongoing work right now. And we also looked at the Canadian Sport Institute in Calgary. This was a consumer perception project, and I'll talk more about this later. This was with the sport product testing department. So just going on to the resource allocation at the Cross Cancer Institute. So the Cross Cancer Institute, as some of you may know, is a tertiary cancer center here in Edmonton. It offers both chemo and radiation therapies. It doesn't do surgeries, but it takes other treatments for cancer. And it treats more than about 5,000 new cancer patients that were treated in 2019. So it's a relatively large center. The project that we did here was to look at optimizing resource allocations in the Department of Radiation Oncology. So this was the hospital resources, such as staff and as well as treatment machines that we tried to look at from a data analytics perspective to see if we can identify areas where resources can be optimized. So in particular, we were trying to develop objective measures of the workloads according to the different services that are provided. And then also try to see the relationship between the services as well as the number of patients that were treated. And then generally looking at the factors that were affecting the resource allocation in different aspects of the department. So just to give you a brief overview of the data that was available, we had daily work schedules, and these were detailed work schedules in terms of where people worked, like the timestamps of time in and time out, and the different units that were worked, and also the number of patients that were treated. This was available for radiation oncologists, as well as the radiation oncology support staff, like therapists, nurses, medical physicists, etc. And we also had work schedules for the LINAC, the linear accelerator treatment machines as well. And so so one way of starting, like Mehadi was mentioning, that data visualization is a big aspect in these projects, because these data sets have, in particular, the one that I'm talking about right now, this has not been looked at in this manner ever before. So, starting off with so here you'll see a graph of the radiation oncology support staff and how they're distributed. And this was valuable from the client's perspective as well. It was interesting to them to see this kind of data plotted in this manner. And so here you can see the full-time and the part-time support staff, so radiation therapist 1, etc. And you can, and here, so for example, if you look at the bar that's showing registered nurse, there's only maybe less than 5 registered nurses that are full-time, and the rest are part-time. And that was a bit surprising for the client as well. So just our showing them this data in this manner was enough to kind of help them understand their data better and see ways where they can improve as a starting point. Another example is, so this is the daily average work hours for the clinical support staff. So what we did was we took all the staff that were available, the different types of staff, and we categorized them into 4 different categories. There was clinical, there was administrative, there was service, and I don't recall the so we had these 4 categories in which the support staff were distributed. And then we took all the support staff within the clinical category in this case, and we computed the daily average work hours for them, for that category. And now just plotting this out again, it just you can see that at the end of 2018, there's a bit of a jump here from the earlier values that are close to less than 6 work hours per day, jumping up to 7. And so this was another point where the clients were interested to see this. And now since this project is ongoing, we are delving further into why this might be the case and trying to see the data through different angles. Another example, this is the radiation oncology support staff. Their average work hours for each work area. So now we're looking at the different work areas that are at the cross. And here, just looking at them from, so these different bars of 2016 to 2020, this was the data that was available, and just computing the daily averages per year. And so looking at this, if you look at, for example, close to the middle over here, you see the RT review. From 2016 to 2020, you can see a clear increase per year. And that's what was expected as well, because the patients, the number of patients and the workload has increased over the years. And similarly, you would notice that for Unit 1 through Unit 9, towards the right of this graph, they're all these units, because they're similar entities in terms of service, they look very similar. However, another thing to notice here was, if you look at Unit 1 here, in 2016 through 2019, it is increasing, but then there's a significant drop in 2020, which again was something that our collaborators were interested to look at, and they're going to delve into these idiosyncrasies a little further to see if they can identify something that can help them for allocating resources better. Moving on, this is radiation oncologists. So there were 28 radiation oncologists for which we had data. And what we've done here is looked at their daily average hours worked. And again, this is split over the 5 years that were available. So you see 5 bars for each, one for each year. And again, here you can clearly see, for example, RO13 and RO19, there's significantly less daily average work hours compared to others. And then, for example, for RO18 here, you can see that there's a drop over the years. So again, visualization has been a very helpful tool. It has helped us to see patterns like these that we can clearly identify and kind of delve further into. This was the linear accelerator machines. So we have Unit 1 through Unit 9. Those are the 9 different LINAC machines that were there. And what I've done here is on the x-axis, you have the years 2016 to 2020. And I'm plotting the yearly average time that each person was treated on these LINAC machines, so time per appointment. Now, for the cross, what we learned from our collaborators is that they, at the cross for the LINAC machines, they usually take roughly about 15 minutes per appointment. And that's what we were able to see in these plots as well. So 2016, 2018, 19, and 20, they will look pretty similar, pretty close to the 15-minute mark, a little bit less, which was expected. But you'll notice that for 2017, there's quite a jump here. So for some reason, in the year 2017, the yearly average time per appointment increased significantly. And that was interesting, again, to our collaborators as well. And then delving further into this, now this is for one of the LINAC units. This is Unit 1. And here I'm plotting the daily average time per appointment for Unit 1. And you'll see here, again, similarly to the previous graph, you'll see that in the early part of 2017, there's quite a big jump in the average time per appointment. So this was interesting, and this is something that we are going to explore further in terms of why this was the case and what can be done about it. So just to wrap up this section, the data visualization we found was a very powerful tool to understand and validate the data sets. And then we also found that simple performance metrics like daily average work hours, these were really good starting points for generating insights that were useful to the collaborators as well. Okay, my second use case that I'll be talking about is the sport product testing at the Canadian Sport Institute, Calgary. Now, Canadian Sports Institute, CSI, it is a nonprofit that is dedicated to building and supporting high-performance athletes. And the project that we were interested in was that we wanted to understand, given the data that we had available, we wanted to understand the relationship between a person's perception of, for example, a sport product, such as a shoe, and their actual kinematic or physiological measurements when they're in an experimental condition. And I'll explain this in a little bit more detail as well. So the data that we had available was this. We had 24 athletes, and these athletes, under controlled experimental conditions, they tested out different pairs of shoes. And so they had these wearable sensors attached to them while they were in these experimental conditions. And so we had measurements for movement, force, and pressure that were available at regular intervals for 100 time steps. And we had about 60 distinct time series per athlete. And so what we were trying to measure here was we also had the athlete's perception of softness for shoe X versus shoe Y. And this was done, this was recorded across 5 different shoe comparisons. We had our target variable was the mean hit rate, which is basically what it is that the athlete is the perception of the athlete in terms of the softness of the shoe, whether that perception is the correct perception, because the experimenters already knew from before which shoe is softer and which is harder. And so is the athlete able to successfully distinguish between the hard versus the soft shoe, was computed as the mean hit rate for each athlete over all the experiments. And the objective here was to see if there's a relationship between the kinematic measurements, the physiological measurements of the athlete, and the athlete's perception, which is measured here in this case by the mean hit rate. So here, just to give an example of one of the time series we had available, this was vertical force. And I've plotted here on the left, you see a high perceiver. So this is an athlete who had a high mean hit rate over all the experiments. So they are classified as what we call high perceivers. And then on the right, you have the graph of a low perceiver. And the blue graph shows the vertical force for shoe when the athlete was wearing shoe A or testing out shoe A. That's the curve for vertical force for a high perceiver for shoe A. And the orange is the vertical force for shoe B for the high perceiver on the left here, and similarly on the right. And so there were some subtle differences between how the high versus the low perceiver, between these measurements for the high and low perceivers. And we wanted to see if these differences are significant and if we can use this to possibly predict, will we be able to predict who would be a high perceiver versus a low perceiver? So then we had to compare the different time series. Recall here that we have two time series, one for SHU A and one for SHU B. So we want to figure out a way to compare these two time series, because it's the difference in these time series that is significant to us. So what we did was we subtracted these two time series to obtain what we call the residual time series. So this is an example of a residual time series for vertical force for SHU A. So this is just SHU A minus SHU B. And this top graph is for the high perceiver. And then this is the SHU A minus SHU B for the vertical force for a low perceiver. So again, there are some subtle differences between these two graphs, which we're trying to hone in on and see if we can predict a high versus a low perceiver. Now here I'm showing the average residual time series plots for 3 perception clusters. What I've done here is I've taken the set of high perceivers, that is the blue curve here. I'm just taking the average of their residual time series for each of these 9 variables and plotting those. And then green is mid perceivers, the average residual time series for the mid perceivers, and red is for the low perceivers. And again, so since this is only a single, this is only the average, and I haven't plotted the standard deviation here, just to note that since our data set was extremely small, we only had 24 athletes, there was a lot of variability in the actual residual time series. So the standard deviations were pretty wide over here. Yeah, just pointing that out. So what we did here was the first thing we tried to do was to cluster these time series. So we did some feature extraction from these time series. We did aggressive dimensionality reduction because again, this data set was pretty limited with only 24 athletes. And then we did we tried a few clustering algorithms on the kinematics time series. What we meant to do here was to see, so we already have clusters based on mean hit rate. And so what we wanted to see was whether the clusters we generate from the kinematics time series, how much agreement do these clusters have? And we found that the best agreement we obtained was about roughly 40%, which was pretty low. But again, given the limitations with this data set, that's the result we obtained. Another project we did, a sub-project we did here was to look at some regression algorithms. So we did a leave one out cross-validation and we evaluated using root mean square error and R-squared. But we found that the models we built, they performed only as well as a baseline model that always predicted the mean value. So again, with this work, what we found was clearly, like from a machine learning perspective, we had a large p small n problem, so to speak. This project was extremely limited because we only had 24 subjects and the data was very high dimensional. We had approximately 60 time series to analyze here. But still, as a proof of concept, it was well received, and then we were able to establish a fruitful collaboration as well. So just to wrap up, I'd like to talk a little bit about some lessons that I learned across during this time. It's been an interesting time here with Clinisys, and I've learned a lot. The first thing I've learned that I wanted to throw out there is that communication is the key. Because you have to understand the problem from the client's perspective, and you also have to help educate them on the machine learning angle and help them to refine their goals to be more objective and more actionable. So I found that was very important. And then on the other hand, you also have to be extremely respectful and cognizant of the fact that the client is really the subject matter expert in this case. They are the ones who know their data. They are the ones who have collected their data. And, so there's a wealth of information that the client or the collaborator has that we need to harness. So communication has to be a back and forth sort of thing. And then we also have to help them understand that there are opportunities with machine learning, but there are also limitations with machine learning. So does ML even fit their use case? And we find that many times it doesn't. All that the collaborators need at this point, at the proof of concept stage, is maybe just some data visualizations, just to help them understand their data better and look at their data in different angles, not necessarily get into the machine learning algorithms, so to speak. And again, with the limitations in the data sets also, many times you can't really apply a lot of sophisticated machine learning in these cases. Another lesson I learned was the simpler is usually better. And so you always start small. That's always helpful to understand the data and to see where the value lies in terms of what you want to achieve. And again, understanding the data and the problem is, for sure, I found that it's more important than trying to apply the latest machine learning techniques. So with that, I will thank you, and Mehadi and I will be ready to take any questions. Just stop sharing.
So first, I have a few quick questions. So first, excellent summaries and lots of interesting research going on. But a question first for Mehadi. Several of the projects, some of my colleagues are working on hospital readmission tasks as well, and for 1 year, for 30-day, 5 years. And one question that I've asked them to try to help them guide in their project is, what do you do with that? Suppose I told this patient will be back in 30 days. I suppose I was completely accurate. What do you do about it? And they said, well, we're not quite sure. We certainly report it, but, and I said, well, what about, would you keep them longer? Would you do more tests? Would you, it sounds like you've addressed that. So I want to drill down on that. Imagine you had a perfect tool that could completely accurately identify who would be back in 7 days. You're saying that they would keep them in the hospital longer? Is that what they would do? Or?
Yeah. So in this particular case, Newmarket, South Lake Regional Health Center was the hospital, fairly large hospital, I think equivalent to what we have in Graynans here, the numbers.
Yes.
What they were trying to do, or they did, was actually to keep these patients longer, because in order for them to get them again through the same channel of hospitalization through emergency was a very highly costly item for them. So if they keep them in hospital for a longer period, means they have to change some of the processing internally that they discussed, but then they can reduce this number. Now, there were other like social factors and so forth that they wanted us to identify. That was phase 2 of the project, which never happened, which was known as case costing. So how much each patient is costing to the hospital. That's where it was coming down to. But yeah, as you pointed out, that the intent was to, or the solution in their mind was to keep these patients who are high risk longer, to do more tests before they are thrown out back into the world.
And the second issue is, how did you validate that? Did you have a a soft rollout where you didn't tell the doctors that, but you afterwards said that patient should stay longer, and sure enough, that patient didn't come back. And this patient, how did you confirm that actually would work?
Yeah, so in our case, in our project, they hired an external auditor or validator because they already had a process in place, and what they were doing with us was replacing that with newer thinking or new model. So they did hire, and then that evaluators or group of evaluators came back and said, well, this is 80% more effective than what we were doing before, some kind of a numerical value. So that it came out. Again, implementation in hospital is still a big issue because the systems are so large and the data has to continuously flow, and that never happens very smoothly. So yeah, that's what they had hired an external evaluator for this particular project actually.
Okay. Good. Very interesting work. Thank you very much.
Thanks, everyone. So just doing a time check here, we're about a minute away from the meeting's official end. So I'd just like to thank everybody so much for joining us today. And thank you so much for the incredible presentation from the folks at Clinisys. Please keep in touch with us. If you have any questions or comments or general enthusiastic words, you can reach us at hello@amii.ca.
And last but not the least, big thanks to Amii, because it just multiplied the amount of projects that we are doing in the ecosystem. So thank you for the teamwork there. And we really are proud of both the partners, Amii and UFA, to handle these projects as we move forward.
We so appreciate that. Thanks.
Thank you.
Thanks,
All
Mehadi.
right. Have a good
Thanks,
afternoon,
Zehra.
everyone.
Okay,
Thank you.
thank you.
Bye-bye.
Take care. Bye.